Welcome to the new lecture on fluid in the area of aerodynamics or in the area of aerospace. Aerodynamics, it clearly says dynamic means it is a changing phenomena with respect to time. Aero means it is like aeroplane and other things. So, it is going to talk about what is happening above the land surface. Right. It is a very interesting phenomena, because when you try to see the Earth's atmosphere, so the flight generally travels at around about 30,000 feet. Normally, they will go in that feet, because here they will not have much of turbulence. So, they will always go 30, 33, 35,000, that is how they go, so that they can travel very fast with minimum resistance. So, now the question which comes to your mind is, what happens to the temperature? What happens to the pressure? Now, how will the thermodynamic property change? Now, when these two changes, what happens to the density of the air? So, all these things come into your thought process. Now, in this lecture and in the next lecture, we will try to understand little bit more on this aerodynamics of fluids. And friends, when we talk about fluids, we clearly saw that liquid is one part and the gas is the other part. So, this becomes compressed fluids, and they are incompressible fluids. So, by and large, they both are linked. So, we will try to put efforts in this lecture to understand more on the aerodynamic property. So, in the content of this lecture goes like this: first, aerodynamics. We will try to see what is aerodynamics. Then, what are the fundamental law of aerodynamics? This will be good for you to understand, because we studied some laws in fluid, and now let us see how does things change, or how is it getting modified little bit to meet out to the requirements where the fluid is compressible. Then we will try to understand lift and drag, because this is very important when you talk about planes, and then aerodynamic profile, then anatomy of an aerodynamic profile, and finally, we will try to see the references. It does not make any sense to classify the study of dynamics of both liquid and gas under the same heading called fluid dynamics, because it is completely a different game, ball game, compressible fluid, incompressible fluid. So, we cannot put them in one topic. So, let us clearly distinguish three. So, one is called as aerodynamics, the two is called as hydrodynamics, and the third one is called as gas dynamics. Hydrodynamics is very important for people in civil engineering, mechanical engineering. Aerodynamics is very important for people in the field of aerospace, and gas dynamics also, it is in the same thing. So, certain difference exists between the flow of fluid and the flow of glass. So, that is why we divide them into three categories. So, therefore, the fluid dynamics is divided into three areas: hydrodynamics, flow of fluid. This can be water or it can be any other fluid. In processing industry, we use, for processing industry and in particular pharma industry, we use multiple other fluids apart from water, but water is most commonly used. That is why all the cycles we study, we always look into the phenomena of steam. Then comes the flow of gas, the last one is flow of air. So, these two are to some extent linked. This is gas of one particular domain, air is the normal one, which is a mixture of several gases. Aerodynamics is a field within fluid mechanics that focuses on the forces and moment. Friends, we saw three things in the past. One is conservation of mass, conservation of energy, and conservation of momentum. Right? These are the three basic laws. We will have to solve any problem in any of these three, or all the three, or maybe two, depending upon your specific requirement. That is what we saw in the laws of fluid mechanics. So, aerodynamics is a field within fluid mechanics that focuses on forces and moments experienced by a body immersed in a fluid stream. So, friends, what happens when we use the body inside water? The same phenomena comes. For example, submarines, same thing comes. Okay. So, when we talk about ship, there are phenomena what we study in aerodynamics can be used in ship phenomena also, right. So, these are mechanical engineering, marine engineering. There in these fields, we are more particular about this aerodynamics, and we try to talk about the forces and moment experienced by a body. When I say immersed in a fluid stream, in the air, the aeroplane is immersed inside a fluid stream. When a body is placed in a fluid stream, it experiences force and moment. When we try to take a body in space, you will try to see these are the forces. Like one, you can see there is a lift force which goes up, lift force, right. Then there is a drag force, right, which is pulling back, drag. If you take a car, there is a drag force. So, drag force, lift force, this lift force works against the gravity. And when you talk about this lift force, you also see there is a moment around the lift which is called as yawing moment. There is a moment along the axis of the drag force. When you rotate it, it is called as the rolling moment. Then you will have a pitching moment. So, if you try to look into this figure more carefully, the blue boundary, whatever we have drawn, is an arbitrary body. So, there is an arbitrary body and it is going against the air. So, that is called as the free stream velocity V. It goes around the velocity. Now, there are three phenomena. So, let us try to take in a free space, a body is going. So, the body will try to first go up in this direction. So, that is called the lift force, right. And there is a free stream velocity coming, there is a pulling back, that is drag, right. Then there is a force called as pitching. So, these are the three forces, right. So, when we try to see in, if you have a hand, which is the same phenomena is common in robotics, you will have a pitch, right, a roll and a yaw. This is called yawing. Okay. Drag force. The primary forces are drag force and lift force. So, drag force, the force on a body parallel to the free stream. So, I said no, it moves like this, there is a velocity going. So, there is a force on the body parallel to the free stream and positive downstream. It is essentially a flow loss that must be overcome by the body to move against the stream. So, what we are trying to say is there is a body moving, there is a velocity coming, this velocity is trying to pull back. So, you have to beat this velocity and you have to go. So, that force is called as a drag force. The stream is nothing but the free stream velocity of air. Next is lift, a force which is perpendicular to the drag. So, this is a drag force perpendicular to the drag force. So, lift is against the gravity. So, here is a gravity, right. The force perpendicular to the drag, often performing a useful task like supporting the body's weight. Okay. This is the lift force. So, when a body is immersed inside a fluid, you will have two forces, which is a drag force and a lift force. Friends, if you take it as a point, it is going to be easy to solve. When you take it as a line, then it is little complex, but you can try to solve. When you take it as a plane, then you will have little more complexities to solve. A point which is defined in x, y, 0, x naught, y naught, z naught. When you take it as a line, it will be x naught and x 1. When you take it as a plane, it will be x naught, x 1 and x 2, x 3. So, it will be a plane, and no body which floats in air is flat. it will have its shape. So, now you see how the complexity step after step after step increases. So, finding out the drag force and lift force for a plane, for an automobile car, for a ship which is moving, for a submarine is a challenge, but it is all derived from a simple basics. Weight. It is a force that is always directed down towards the center of the earth. The distribution of weight and the center of gravity also changes. So, this is the lift force, this is the weight force. So, lift is represented by L, weight is represented by W, drag is represented by D, and thrust which is there is represented by F. So, what is thrust? So, when there is a force which is pushing this body behind, so then you get the thrust force which moves forward, right. So, that is why if you see in the fighter plane, when it goes very high speed, it will release a jet of air. When you look at the sky, you see a straight line there, because the air is released, the combustion gas is released into the atmosphere with very high velocities. So, it is not able to diffuse very fast. Over a period of time, it gets diffused. So, that is given for the plane to move, that is called as a thrust force. The fourth force which is going to be there is the thrust force. To overcome the drag, the aeroplane uses a propulsion system to generate a force called thrust. The direction of the thrust force depends on how the engines are attached to the aircraft, right. It can be on the wings, it can be on the tail, depending upon your requirement. And if you look at the boat, when you are trying to go by a rowing boat, you will have a controller at the back. So, you can try to change the direction of the boat by changing the position of the flap which is there at the back. Right. In the same way, in a plane also what happens, you can try to control the direction of motion to some extent by changing the thrust force exit and wing direction you can try to change. Okay. So, the four forces which come into existence are drag force, lift force, thrust and weight. Four are there. Now, you should understand, if a plane has to get that lift of 180 people sitting in a plane, it has to get the lift. So, then you should understand what will be the thrust, it will be phenomenal, right. The lift is against the weight, then this has to not only lift it, but also push it in the forward direction, thrust force. Now, friends, think of an engine which is there, how much of thrust force it has to produce for a plane to fly. In the ship also it is the same story. If the free stream is parallel to the intersection of vertical and horizontal plane, then it is called as the principal chord line of the body. So, you can see here, this is the vertical plane stream symmetry of symmetry, this is the horizontal plane of symmetry. This is like this x and y axis. So, now what are you doing is you are extending it. Right. You have a paper, now this paper is opened, that is all, it is almost like this. So, this is the vertical plane of symmetry and this is the horizontal plane of symmetry. So, a body which is there, so you can see here, this is a blue one is the body. So, this body whatever is there, it is trying to get moved. So, if the free stream is parallel to the intersection of vertical and horizontal plane, then this one is called as the chord line, principal chord line. So, this is a body, this is the body which is also there, and this line is called as the principal chord line, right. So, this is a body. So, the body is trying to swing. So, you can see here, this is the doubly symmetric body. So, this one which moves to this position. The body experiences a drag only with no lift, side force or moment. The body experiences only a drag force. Friends, what you do an analysis for a plane and what you do an analysis for your car is completely different, because the car is supported by a road. So, the car need not have the lift factor at all, and the weight whatever is there, it is resting on a road. So, now what is more important is the drag and the thrust. So, that is what we are trying to explain here. The body experiences only drag with no lift, side force or momentum. So, this is not there, this is not there for a car, and this is also not there for a car. So, it is only this way. The body will have an asymmetric orientation, and all three forces and three moments can arise in principle. This is an important point. So, the fundamental law of aerodynamics was started with Bernoulli's theorem. Bernoulli's theorem is a fundamental relationship in fluid mechanics named after Daniel Bernoulli, who published a hydrodynamic textbook in 1738. It states the fundamental relationship in fluid mechanics that connects pressure, velocity and elevation in the flowing fluid. The theorem is often derived from the integral relationship for a controlled volume or by integrating Euler's equation along a streamline. We saw what is streamline, streak line. So, what are the assumptions here? The viscous effect are assumed to be negligible, which is not there in air. In aeroplane, the viscous forces, the air density changes, the viscous effect also changes. The flow is assumed to be always steady. The flow is assumed to be incompressible. The equation is applicable along a streamline. So, these are the assumptions. These assumptions are major assumptions. In reality, today we are trying to ease out one or the other assumptions, and we are trying to solve the problem. So, the Bernoulli's equation is represented in this way, where you have P is the pressure, this is pressure, this is density, V is the flow velocity of at any given point of time, G is the acceleration due to gravity, Z1 is the elevation height at a specific point, which is equal to, this is the initial point, this is a final point, and it is said to be a constant. The continuum equation which is used here, the continuity equation is a fundamental principle in fluid mechanics that expresses the conservation of mass for a fluid flowing. It considers a local mass balance equation derived by considering the limits of vanishingly small control volumes or fluid particles. So, it is simplified. So, the Euler in 1757 gave this general equation, which is the change in density with respect to time plus the divergent operator multiplied by the velocity vector is equal to 0. So, the divergence operator, we can get this divergence operator while solving problems. Lift, when we talk about lift, this is the typical aerodynamic profile. This is called as aerofoil. So, it is not a flat plane, it is having a curved surface, right, aerodynamic, it is called as aerofoils. Okay. Lift, the lift is a fundamental aerodynamic force because it has to lift up, experienced by the body immersed in the fluid stream. It is defined as a resultant force component that is normal to the direction of flow at infinity and typically pointed upwards. So, it is defined as a resultant force component that is normal to the direction of the flow at infinity. So, it is the normal to this drag direction is the lift, and typically which is always measured upward. And when the plane moves this way, that way and all, the lift angle changes. Okay. So, it is given by the equation CL, which is nothing but the lift coefficient is L L is the lift, divided by half rho, which is the density of the air or water, V square is the velocity, AP is the area, which is calculated as B into C. Again friends, here what we are calculating BC, which is, just assume that it is a flat plate. So, this is trying to calculate the area B and this is going to calculate the area C, but in reality you have a curved surface. So, the lift, whatever we find out, the lift coefficient is generalized one. So, if you see here, the thickness of the aero profile is given as T, and whatever is the width, if you try to say B is the span width in a plane, this is the width of a wing. So, that is B, and the thickness is the, suppose if the plane is going like this, you have a wing, this is the thickness, and then there is a chord length C. Okay. So, the plane form of the area BC will be this. This one is the plane form, and the air always tries to hit at the velocity like this, and there is an angle which is called as angle of attack alpha. So, this is very important. Angle of alpha tries to decide how do you get the lift which when it goes up. So, alpha is a very important parameter. This is called as angle of attack. The lifting bodies, airfoil, hydrofoil or vanes, are intended to provide a large force normal to the flow stream and as little drag as possible. So, drag, if it is reducing, the resistance is reducing. If the resistance reduces, you will get a higher velocity. So, this is the lift, this is the upstream, this is the upstream. So, you have a aerofoil which comes like this is called as the upstream, which goes like this is called as the downstream. So, upstream and lower stream. So, now this is the aero profile and the lift is always in the upward direction. So, here above the plane you will have a low pressure, high velocity, below you will try to have high pressure, low velocity. So, the upstream travels a longer distance and the lower stream travels a shorter distance. This tries to give the lift. So, the lifting body, aerofoil. So, the same thing happens for a ship also. So, now we are talking about a plane, ship also we try to do almost the same, but the upstream and downstream, long distance, short distance may be equal or it can be varying. The lifting body are intended to provide a large force normal to the free stream and as little drag as possible, because the drag is the resistance. The first theory of lift was proposed by Lanchester, W. Lanchester, F. W. Lanchester. The modern aerofoil theory dated from 1905, where the Russian hydrodynamist N. E. Jonkovsky developed a circulation theorem for computing the aerofoil lift for arbitrary camber and thickness. So, he developed this and it came into existence. So, 1905 you see the theory was there. The next force is the drag force, right. The figure is the same. The only difference you have to note down is the drag force. Lift is this way, which the air is flowing in this direction or in at an angle. So, this is the drag force. Drag is one of the primary force experienced by a body immersed in a flow stream. So, if you have undulations on this, you might have a lot of air resistance, and if the undulations are very small, then there is a possibility the smooth streamline of air whatever is there, you are breaking it. So, you can have it as an advantage. It is defined as a resultant force component on the body that is parallel to the free stream direction and points positive downstream is the drag force. The drag force or the drag coefficient can be figured out by CD is equal to drag divided by half rho V square A. A is B into C, as we have already seen. So, basically what you do is you have a drag coefficient which many a times is given in the examination, and then you will try to multiply by this factor which I call it as x. X is equal to drag. So, through this you can try to find out what is your drag. So, in the previous one we saw lift almost the same way. So, the drag of some representative wide span nearly two-dimensional body is shown in the figure. For a square cylinder, for a diamond-like cylinder, the square is rotated by 45 degrees. So, for example, this is rotated by 45 degrees. You get the CD value is lower. What is CD? CD is the coefficient of drag. Then if it has a half tube, it is 1.2. When it is having a convex shape or inverse of half tube, you see 2.3. So, now just by changing the shape, you will try to see how the CD on the frontal area changes. Now, if you try to have a half cylinder, you see it is 1.2, which again I just changed that is why you see the values are very low. So, if you have a closed cylinder or a half tube, cylinder is full solid, tube you will have is a small, you will have internal diameter, external diameter, you see. So, now in aeroplane you have a solid or you have a hollow tube, the CD is almost constant. So, it is better to have a reduced weight. So, we always go for hollow tubes, right. Then if you have a equilateral triangle, it is 1.6. So, if you see here this one at an angle of 45, it represents the same. So, it is 1.6. So, rather than having a square, you can have a rectangle. When the surface area is large, you see it is 2. When we try to have a plate like structure, it is 2. Plate, why? Plate is very important because in the wings, if you have a vertical wall, it is like a plate. So, then thin plate normal to the wall is 1.4. This was 2 is this way, this is this way. So, that is why in a plane you try to have this and this. When you have a hexagonal, it is 1, and here hexagonal is very difficult to fabricate. So, that is why we try to have this aerofoil in this direction. So, in drag there are various types of drag, which is very important for you to understand. It is not one full force. Drags are of 3 types. One is you will have parasitic drag, then you will have induced drag, then you will have wave drag. Okay. The wave drag, it looks like wave, they are creating wave, which comes into play when shock waves are developed close to the surface of the aircraft in transonic or supersonic flights. It does not happen in one wave, which is normally seen in the ocean also. So, that is what is wave drag, which comes into play when shock waves are developed close. Shock waves are, there is a disturbance in the wave. So, that is called as shock waves are developed close to the surface of the aircraft, right. So, it operates in very high speed, supersonic. We discussed about Mach number. So, in the Mach number classification, we have seen supersonic. So, then let us try to see the other two. Parasitic drag. So, it is composed of form drag, skin friction drag and interference drag. In form drag, which is a result of aerodynamic resistance to motion due to shape of the aircraft. So, form. So, that is why we always try to say a plane something like this, and then you have a wing, right. This is called as form drag depending upon the shape. Skin drag is which is due to the smoothness or the roughness on a surface. So, this is what I said, you take a profile wing and then you have undulation on the surface, that is skin friction drag. If the skin friction is too tight, then it is very difficult. What happens? It gets integrated into the profile and the wind blows above it or flows above it. So, which is due to the smoothness or the roughness of the surface of the aircraft. Interference drag is between form and skin is interference, which may occur where surfaces with different characteristics meet, such as wing and fuselage. The center portion is called as the fuselage, this is the wing. This is wing, this is fuselage. Okay. Where it meets, it is called as interference drag. So, form happens here, this is form, predominantly this is form which happens here, and then wing happens here, or the skin happens here, then the interference happens here. The induced drag, which is a secondary effect of producing the lift, is induced drag. So, drag, all these things are resistance to flow. So, you have to reduce as much as drag as possible. So, you have form drag, skin drag, interference drag, then you have induced drag and wave drags, right. These are all normal drive which is there, except for this, which is for high speed flights. Let us look into aerofoil. An aerofoil is a type of lifting body. They are specifically designed to provide a large normal force to the flow stream. So, they are provide a normal force to the flow stream, which is lift, and a very little drag. Drag is nothing but resistance. As I told you, on the top you will have high speed and reduced pressure, in the bottom you will have low speeds and increased pressure. Conventionally, aerofoil design has evolved into shapes resembling a bird's wing. Typically, relatively thin, which is thickness to chord ratio. We saw what is chord, this is chord, thickness is the T we saw, which is T by C, is usually less than 0.24, with a rounded leading edge and a sharp tailing edge. So, this is a aerodynamic profile. We could have seen why did we go for this. You have seen through CD coefficient, we saw that why it has to be like that. A lifting aircraft cruising at low angle of attack. What is angle of attack? Alpha, right. A lifting aircraft cruising at low angle of attack where the lift is much larger than the drag. So, the maximum lift to drag ratio for the common aerofoil is around about 20 to 50. So, the ratio lift to drag 20 to 50, lift to drag. So, drag has to be as small as possible, lift has to be as high as possible, so that you get to have a higher value. So, when the plane goes like this, when it is trying to lift, you will see lift is on the higher side, then you will see the air pressure, higher pressure of air is low. So, that will try to press and this will try to go up. So, when we try to look at the anatomy of the aerofoil, this is alpha, angle of attack, this one is called as the leading edge, trailing edge, lift, drag, chord length, which is the perpendicular, no? So, it is a straight line, chord length, and this is the deviation of a chord length is called as the camber line. So, these are all very important. When we try to take it for the car also, almost the same thing comes. So, we will there will be some modifications, but interestingly in a car you will not have a lift force, right, drag force is dominant. So, when you go into water, it is again the same story, but the lift will be on the higher side and the submarine will try to go down. So, the leading edge is the foremost point of the aerofoil. The part is facing on the oncoming airflow. Tailing edge or trailing edge located at the rear end of the airfoil, the trailing edge is where the airflow recombines after passing over the top and bottom layer. This is the trailing. So, the stream comes here, the stream goes here, then it gets recombined. Chord line, the chord line is a straight line connecting the leading edge to the trailing edge of the aerofoil. Leading edge to the trailing edge, connecting straight line. The angle of attack is the angle between the chord line, this is the chord line, right, between the chord line of the aerofoil and the incoming airflow. So, you saw a chord line like this and there is an airflow. So, this is alpha. Adjusting the angle of attack allows the pilot to control the lift and drag force acting on the aerofoil, which is crucial for takeoff, landing and maneuvering. So, they always try to talk about the angle of attack, right. So, camber length is the curved line, camber length is a curved line, this is a curved line, is a curved line equidistant from the upper and lower surface of the aircraft. So, this is the camber line, upper and the lower, right. It is the equidistance from the upper and the lower surface of the aerofoil, which is used as a reference to quantify the amount of camber present in the aerofoil design. So, these two are very important, camber line and angle of attack. There are transient stages in the development of lift. So, I have classified it as A, B, C and D. So, A is startup, where the rear stagnation point of the upper surface is there and there is no lift at all. In B, there is a sharp trailing edge induces separation between the top and the bottom, and there is a small vortex which is created, which creates a slight lift. So, the starting vortex is shed and streamlines flow smoothly from trailing edge. The lift is now 80% developed. So, it is almost lift is 80% developed. The large vortex shed far behind the trailing edge, now very smooth, the lift is fully developed. So, now you see the vortex, how it is getting and how the vortex is moving. So, these are the transient stages. So, here in A there is no lift, it is at normal, slight lift, there is a vortex behind the trailing edge, then there is this trailing edge is going back. So, there is a lift getting developed 80%, and fully developed lift is the vortex is very far behind. So, at a low angle of attack to the plane, the rear surface have an adverse pressure gradient. At low angle of attack alpha, okay, the rear surface have a adverse pressure gradient, but not enough to cause significant boundary layer separation. The flow pattern is smooth and the drag is small and the lift is excellent when it goes like this angle of attack. At a low angle of attack, when the angle of attack is increasing, when alpha is increasing, the upper surface adverse gradient becomes stronger and generally a separation bubble begins to creep forward on the upper surface when the angle of attack is increasing. The angle of attack generally takes a value between 15 to 208. The flow is separated completely from the upper stream. The aerofoil is said to be stalled. The lift drops off markedly, drag increases markedly, and the aerofoil is no longer flyable. Okay. So, this is what they are trying to talk about. So, you see a vortex getting created, then when the angle of attack is increasing, the upper stream adverse gradient becomes stronger and generally separation of bubble happens. So, the application of aerofoil. So, we always think the aerofoil is smooth, but in reality if you look at whales and sharks, it will always have some undulation on the surface. So, the wings inspired by the humpback wave, unlike most whales, the humpback whales has tuber cells or bumps on its surface of the leading edge of its flipper. Flipper is what is there in the projection. The scientists tested this idea under a standard wing with periodic bumps glued on this leading edge. So, the report says that there is a 40% increase in the stall angle compared to the same wing without bumps. So, the air to drag ratio increases. The concept comprises for commercial applications such as wind turbine blades today are made with this tuber cells. So, these are structures which are there. So, if you go back and see, we studied about the drag, which is skin friction drag. So, that is reduced to a large extent by doing so on the surface. Friends, in this lecture, we saw what is aerodynamics, then we saw the fundamental law of aerodynamics, Bernoulli's law. We understood what is lift, what is drag, and what is airfoil stating and its application. These are the references which we have followed for preparing this lecture, and thank you very much.